I kind of feel like the least and usually the most I can do in any talk is expose people to the Scottish spelling of the name Rory. So it's originally Gaelic, and it means the colour of blood, and Rory is an anglicisation of the Gaelic. There you go. If I've mentioned one thing, that's it. Okay, and so I am a computational psychologist, or at least one in training, nearing the end of my PhD. And I kind of thought what would be most interesting for this conference is to sort of expose anyone who hadn't been exposed to computational psychology before, to the kind of methodology and also the ideology we use, and then invite people, hopefully through the course of the talk, to help me propose experiments that people might actually want to do online or in the lab that I can help with the data pipeline. So what is computational psychology? Okay, we kind of start with this premise, maybe familiar to computer scientists, mathematicians, but quite unfamiliar to psychologists, of we can learn a lot about what's going on inside the head by studying the environments we encounter outside of it and the computational problems that they involve. So this is sort of a highly schematic illustration of the jungle. It's a painting by Rousseau. And the idea is that by thinking about ecologically relevant questions that a human or an intelligent agent might have had to overcome, like, is this safe to eat? Will this eat me? We can study people's behavior empirically and try to think about what are the computational strategies they're using to overcome these problems, and ergo what the brain must be approximating in some way. So these are sort of these are statements at a computational level, meaning they're about families of models and the different behaviors that those families could or could not model. This is a kind of viewpoint that I think goes back in a lot of fields to different thinkers. So most notably Noam Chomsky, who we heard about earlier, and also Tinbergen. I mean, really it goes back to Aristotle. But in neuroscience, David Marr kind of famously put forward this way of thinking about explanations. You know, at what level is the question you're asking, and at what level is the explanation you're giving? And so he kind of emphasized the importance of this computational level, in which, when analyzing an information processing system, we think about what the goal of the computation is, why it's appropriate, and then provide a solution in form of a logic or a statement about classes of model by which that solution could be carried out. Always with an emphasis on adaptivity, thinking about problems that are ecologically relevant, that this information processing device has been designed for or adapted towards. And so this sort of quintessential example is of a cash register, maybe the first example. Thinking about the situation of going into a shop and, you know, collecting a lot of items, arriving at the till, and what are the properties of that we think are important? What is the goal of a computation like that? And so, you know, by this kind of process of analysis, we can come up with a series of properties that we believe are important or fundamental, or that we would be very annoyed with if that didn't happen. So, for example, if you arrive with nothing and people charge you, that occasionally happens when you're exiting a country. They sometimes charge you a kind of a tourist tax. It feels you're very annoyed at that. Also, if you put like the Kit Kat and the crisp in a different order, it could cost a different amount. That would be extremely annoying. If you kind of shuffle them forward in different groups, that shouldn't seem to make a difference. And also this kind of idea that if you refund something exactly as you bought it, it should equal zero. And sort of the Marian analysis would then translate that into a logic. And so here we have a number of elements of that logic, and then kind of recognize that or equate that with the formal system of addition, basic arithmetic. Now, that's a toy example, and I'm sure many of you might have seen it before. It's the first one in Marr's book, but then the birth of the field of cognitive science was really in 1957 with Noam Chomsky proposing this idea of recognizing a language as being equivalent to thinking about the grammar that generated the language, and then trying to think about the type of logic, or in this case, the restrictions on the class of automata that could calculate that logic. And, so this kind of spawned many different fields or directions, but in cognitive psychology, I think what we're most interested in is, okay, well, what empirical behaviors do we see in the real world that would give us a sense on what is the sort of computational strategy, what are the set of computational strategies that humans can give. And then, the kind of Chomsky hierarchy has been enlarged substantially since then. And there's this active, ongoing research program, which is kind of like, it's an empirical program. People are studying computational activities they think are important, coming up with experiments they think test those activities, studying them in a lab, and at the same time trying to come up with computational models for those, and those computational models are also then subject to mathematical analysis. And so the kind of question is, for different domains of cognition, what is the balance between the inductive biases that a learner brings to the problem versus the flexibility of the learning algorithm? We heard a little bit about that 2 talks ago. And what does this distribution look like of the things humans do that are important? Is it the case that for most of the things that humans are doing, there's sort of one family of models that are completely sufficient? Or are there examples from sort of less computationally feasible classes? Okay, and so what about the jungle? What about more complex ecological problems? I think the great successes of the field have kind of mainly been derived from these highly artificial laboratory-based experiments, kind of through the 80s, 90s, and noughties. And now we're starting to get to a phase where we're thinking about more complex stimuli, more complex environments, and how to sort of take this idea of computational analysis into these areas. So I was going to give a series of examples from my own work, again, just to give a flavor of the experiments that we are conducting. So this question of will this tiger eat us or not? I think the first thing to do is recognize that this is an inductive problem. It's underdetermined by massively underdetermined by the data. And I think we are imagining here that this is a real life scene rather than a painting by Rousseau. And people have formulated this as a problem of probabilistic inference. Okay, so what is the probability of this latent property will eat me, given the data we've seen? Let's encode that as X, or let's write that down as X, and our background knowledge, the set K. The simple operations of the probability calculus, one can invert this into a generative model. And now we have the kind of goal of the research program is to study people's behavior and study the predictions of different models and work out which kinds of computational strategies capture normal human behavior. Okay, and so in the case of categorization, there was very influential work, I guess, dating back to Wittgenstein, but Eleanor Roche at Berkeley and Robert Nosovsky. And so there are kind of a few different computational strategies for how we might calculate something like this, right? Like, what is the probability that this will eat me or not? And so in one family of models called exemplar models, the stimulus, let's say here it's a tiger, is compared to every single stimuli that we've encountered before, stimulus that we've encountered before, and the subset of those that are significant, in this case, that could also eat you, like sharks and maybe big snakes and tigers, are used to come up with a kind of a generative model, this likelihood function here, of whether this new stimulus will eat us or not. And these have always been contrasted with what are called prototype models. And so in a prototype model, there is this kind of ideal, or usually taken to mean more like an average of previously encountered category members. And the computational strategy is comparing this new stimulus, how likely that would have been generated under the old prototypical model. Okay. And so, there's been great back and forth between these two classes. One can show that they can both be captured by, well, let's say that's a hierarchical Dirichlet process, if people know what that means. But in general, they're both a case of mean estimation, right? We have algorithms for those, even in robust settings, that fall in the category P. But is that really all that's going on? Could you confidently conclude that that tiger will eat you because it looks quite a lot like the previous members of that consequential region? in psychological space? Probably not. There seems to be a lot more going on here. Like, for instance, there's something going on in the environment that that it seems to be affecting the tiger, and could then affect that decision of whether it's going to eat you or not. And this is where my own work has sort of begun, the taking off point. And that's something like, the theory of what's going on in the environment is very important to these questions or queries that we're going to ask about it. So one could look at the sort of direction of the leaves here, maybe the rain and the tiger's stance and its eye. You see that tiger looks quite scared, and it might be that there's a storm going on here. And indeed, Rousseau's title for this is "Tiger in the Storm" brackets surprise exclamation point. So something intuitively about that would lead you to think that tiger is much less likely to eat you if approached appropriately or avoided. And this idea of constructing an intuitive theory of the environment is what I've been focusing on in my research, and corresponds very closely to the idea of a theory from model theory, in which we have a set of entities, a set of features, functions or properties of those entities, and a set of relations. That's the content of our intuitive theory. And now those relations could be over the integers, they could be over the reals. That's up to the choice of, that depends a lot on the choice of environment or stimulus. And in general, probabilistic inference over these models could be thought of as solving for a stochastic block model. It's slightly more complicated than that. We're in a non-parametric setting. We involve features as well as relations. But, stochastic block models do have this strange phase transition property. But in general, the types of complexity we're thinking about are in NP. But do we even still have enough information to decide what's going on? I mean, these are like coming up with understandings like these are extremely complex for an extremely underdetermined setting. My PhD thesis has been on how we need to bring even more data to bear on these scenarios. And so in a mode of reasoning, maybe similar to analogy or analogical reasoning, I sort of proposed that in the small sample regime, we're relying a lot on our related theories from different environments and bringing them to bear on the consequential problem. Okay, and so what can we investigate from such a setup? So a few results we've had in very schematic and preliminary form. So there's something called the relational shift. And I think as mathematicians and physicists, this will also appeal to people here, where first predictions, inferences, understandings are made on the features of the system. But with more experience, more expertise, or even in development, people and children increasingly base their predictions on deeper relational similarity, this sort of relational component of that intuitive theory, or indeed more explicative relational theories themselves. And so I just wanted to kind of show the typical experiment that was done in the sort of late 80s here, which is where if you tell children these kind of stories, you tell them stories involving a seal, a penguin, and a dog. I think one is like nice to one and horrible to the other. And you tell them a subsequent story in which the animals are kind of similar. Let's say they're roughly belonging to the same, well, I don't know what category means here, but they're very physically similar. Then children can correctly fill in the theory. They make the right predictions as to how the story is going to go. However, if the animals are highly physically dissimilar, like the seal is associated with a lion, the penguin a giraffe, and the dog with a camel, they fail completely to generalize that knowledge. And so we found something like this in the lab, and this is going to be a kind of schematic form. But if we think of each theory as, well, we're thinking of the state of the learner's knowledge being a probability distribution over theories in that kind of conceptual space, the more theories you have that share the same relational component but maybe different features, the more strongly that relational component of the theory is going to influence your predictions. So there's something like, so let's say an intuitive theory of magnetism, maybe encountered when like exploring one's fridge, is that magnets seem to have this strange interaction with each other. They interact with iron objects and they don't interact with plastic objects. Iron objects don't interact with each other. Here's a simple representation of that theory. It looks kind of like a stochastic block model, right? So this is each entity that we've encountered now. It can be grouped into these classes, and the interaction between entities explained by the class. Then let's say you move to America and you kind of realize the political system is a little bit similar to the magnet system, but looks nothing like it, you know. But there's these Democrats, you know, they're sort of interacting a lot with themselves. Republicans seem kind of solid together, interact with Democrats, and then there are these independent characters who I still frankly don't really understand. You know, look nothing like magnets, but that relational structure I think is actually very similar. And then, you know, you kind of introduce to the internet. My supervisor suggested this one, which is telling, because I think I'm a Luddite in this category. I don't really interact on social media. We have influencers interacting with each other. You have these sort of lurkers, I think they're called. It's a horrible name, but who are just receiving content. And so I think you can see that with the development of distributions over this conceptual space, the importance of these features is decreasing, but the sort of relevance of the relational component of the theories is maintained. So that does model, and we've seen in experiments, this is what arises, the kind of relational shift. More of a novice-expert shift than the original developmental one that was proposed. There's also something that I think is very compelling, which is the idea that in the small sample regime, drawing on analogies is extremely important. Either if you're explaining to someone without much, in fact, with the last two presentations, you know, we saw so many analogies, it was great. If you're explaining it to someone, or if you're trying to figure it out for yourself, if you have loads of relevant analogies, it really improves the kind of the ease with which you're developing the first kind of stages of theory. But then as your knowledge increases, as your experience in the new system does, then one tends to rely more on theories. So, you know, in this scenario, initially you might be thinking of something like, okay, cats in the water, probably not going to attack. But then there's a jungle book, there's that tiger who's always eating humans. But as you're out there in the sort of complex ecological setting, the relevance of those past analogies is decreasingly helpful. Okay, and so my talk had consciousness in the title, so I should kind of mention consciousness and how I think my work might relate to it. And so really here, what I'm thinking is there's this, what I think of as a fundamental component of consciousness, which is reasoning about our theories themselves, developing theories about our theories themselves. And so there you go, I just showed that, you know, an algorithm for solving this theory is in NP. So that's sort of consciousness is NP hard, right? That's the lower band. But when I'm moving more into thinking about exactly how to set this up in an experimental and a modeling context, I'm really open to people's thoughts and advice for what are particular experiments we could run, how to translate thought experiments into the lab. So there's clearly something, if we had the extended theory, it would just reduce to the same problem of probabilistic inference. Now we're thinking about meta-theories. There's something fundamentally different between these two levels, and you know, namely that the agent has full access to the hypothesis space at the current level, but not full access to the next one. And so people have come up with really interesting and cool ideas about what this might mean. You know, I think going back to Chomsky, there's the nativist approach, which is actually just to set a complete upper limit on the size of the hypothesis space. But I'm proposing this as a kind of empirical question, and a couple of the cool kind of first sets of findings that have been coming out have been thinking about this being more in terms of the better way to think about modeling human behavior is at a slightly different level of analysis, and that's in terms of resource rationality. And here we've had kind of theories about sampling. You know, maybe the appropriate model is approximate inference, and maybe we can model these aspects of human behavior, like anchoring or a lot of behavioral economics, by thinking resource rational terms. And then there's this kind of other set of more new work, including the Dreamcoder work by Kevin Ellis, which thinks about the hypothesis space just being so intractably large, like the space of all programs in the lambda calculus, let's say. But modeling the human journey of discovery and interaction through things like compression, you know, the expressibility of solutions as program synthesis, and the role of simulations and dreaming in that context. So those are the first few sets of cool ideas that have come out from thinking about that. So that's the end of my talk. I'll thank my colleague Dan Nicolau, who was going to be here talking with me, but regrettably couldn't. I'll also shamelessly plug, we're running a conference in a couple of weeks on Crete, which is filled up now in terms of speakers, and quite a number of people here will be speaking there. But we'll be opening for registration too, so come along, and in future years, do submit your work. We'd love to hear from you. Thanks to my various sponsors at various institutions, especially to my PhD supervisor, Tom Griffiths. There are some references, and I'll take any questions. Thank you.